Hello, welcome back after the long break. I hope you guys had a happy new year and have a happy new year this year. We're going to be continuing on with section 4.4 from chapter 4, where we began talking about probability. And we've been doing the addition rules of probability. We're going to be heading into the multiplication rules. So this is our objective for today, to find the probability of compound events using multiplication rules. And this is easy peasy. You're going to love it. Easy. So let's get going and talk about where we left off last time, which were the addition rules. And the way to tell when you use an addition rule and when you use a multiplication rule is this simple word in between here, or and. Addition rules are used to find the probability of A or B for both mutually and non-mutually exclusive events. If you recall, mutually exclusive events means that they cannot occur at the same time. PA of A and B, that's when we're going to be using the multiplication rule. So the basic multiplication rule is used for finding the probability of A and B, probability that event A occurs in the first trial, and probability of event B occurs in the second trial. Or you can think of it as two or more events that occur in sequence. We're going to be using the multiplication rule. Now, one thing to keep in mind, this is a key concept. If one of the probabilities, so the probability event A, somehow affects the probability of the second event, you have to take that into account. And we'll get into more into that tomorrow. Today, we're just going to kind of introduce it and ease back into the old statistics. So some examples of independent events would be rolling a die, then rolling it again, drawing a card from a deck, replacing it, and then drawing a card from that same deck, and flipping a coin, then rolling a die. You can see that one would not affect the other. One of those probabilities would not affect the other. Now, just to give you a preview, if I drew a card from a deck and then didn't replace it, that would affect the probability of that second one because there'd only be 51 cards to choose from. Just kind of a little foreshadowing. So let's talk about dependent and independent events. Two events are independent if the occurrence of one does not affect the occurrence of the other. That's all that is to it. And we're going to talk about dependent events tomorrow, but if an event is not independent, it is dependent. Multiplication rule 1. This is called the informal rule, and it's when they are independent. This is the most important thing about this rule. It says if events A and B are independent, then all you have to do is take the probability of one and multiply it by the probability of the second one. Here's some examples. If you flip a coin and then you roll a die, find the probability of getting heads on the coin and a 4 on the die. So when we set this up, the probability of the heads, and notice it's highlighted, 4 is the probability of getting heads times the probability of rolling a 4. Notice the color coordination. So to get a head on a coin, it would be 1 out of 2. To get the probability of rolling a 4, there's 6 possible numbers on a die, so you'd have 1 out of 6. Then to multiply fractions, oh yes, other fractions. Oh, we love them. No, we love it. 1 times 1, 2 times 6. You multiply straight across. So you'd end up with 1 out of 12. That's it. Easy peasy, right? So let's try another one. A card is drawn from a deck and replaced, and then a second card is drawn. Find the probability of getting a queen and then an ace. So there's 52 cards in the deck. Probability of getting a queen. There's 4 queens out of a possible 52. So that'd be 4 out of 52. Then we put that one back and we'd still have 52 cards in the deck. There's 4 aces in the deck. So we'd have 4 out of 52. When we multiply straight across, we get 16 out of 2704. Reducing, you get 1 out of 169. If you notice back at this point, I could have reduced both of these fractions to 1 out of 13 times 1 out of 13. I probably would have done that just because I don't like getting all these big numbers and then trying to reduce again. I do know that big numbers need love too. Do I ever? But if you could possibly put your fractions in lowest terms at this stage, it will help you out. All right, I want you to try this next one about the urn containing 3 red, 2 blue, and 5 white balls. Got a lot of balls. You're just going to do this one, and I'm going to check that one to see if you understand the multiplication rule in your notes. How about several events? Now this is pretty easy. In general, the probability of any sequence of, here's that word again, independent events is simply the product of their corresponding probabilities. So we have the probability of A and B and C and yada, 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 yada. We're just going to take the probability of A times the probability of B times P of C and so on all the way down the line and multiply them all together. A small sample is selected from a large population and the subjects are not replaced. We treat them the same as the probability changes very little. So in other words, they're saying instead of not replacing the deck of the cards, that would make a difference. But if I have like the population of the United States, which is millions and millions of people, 4 out of 10 million 5 is going to be very close to 4 out of 10 million, because in this scheme of things, it's not going to change your probability that much. It's still going to be very close to zeros. Thus, replacement of the small sample becomes negligible. Here's an example of compound independent events and using the multiplication rule. So we've got a Harris poll found that 46% of Americans say they suffer great stress at least once a week. If 3 of these people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. So we're going to let S denote stress, and the probability of S and S and S is the probability of S times the probability of S times the probability of S. That probability is given in the problem, 46%. We're going to go ahead and change that to a decimal, 0.46, and multiply it by itself those 3 times. And that's going to give us approximately 0.097. That's it. It's very simple, very straightforward. When we get into conditional probability tomorrow, that's when you have to be a little bit careful. I want you to try this last one on your own. It says approximately 9% of the men have color blindness that prevents them from seeing red and green. If 3 men are selected at random, find the probability that all will have this type of red-green color blindness. I have trouble finding the difference between navy and black, but that's a different story. So finish up these notes, and I will see you tomorrow for part 2.